Hey, welcome back to part 2 of this video series on single-phase inverter. We were solving a particular problem from a textbook. So let's continue with the further development of more interesting cases. At this point, I would like to see the effect of different modulation index on the output voltages. In this particular case, we had a modulation index of 0.8. Now you know that the modulation index and the output voltage has a relationship up to a certain point when they remain linear, and then after a certain point the output voltage gets saturated. That means it's like a hysteresis, not exactly hysteresis, but I would say it increases with the increasing modulation index. The output voltage increases, and after a certain point it starts to bend or saturate, so to speak. So this effect we will be observing from different simulations. Now this is particularly interesting because in this case we need to run a number of simulations or batch simulations. Of course, we're not going to do this by hand. That means we will not set one particular value of 0.8 and then save the simulation results. Or rather, we will write the script here to run the simulations automatically and save the variables so that we can plot them later and analyze the results. So for that case, since I want to save the data, let's take the variables. In this case, it would be the output voltage and current to MATLAB so that we can process the data further. And for that, we need an output. Remember, the first one was the VM1, which is the output voltage. Let's just call it Vout. And the second one, since I am only interested in the current, I will remove the resistor power and just take the current to the workspace. I'll call it iLoad. And to workspace. First one is Vout as time series, the format of save. This, let's call it iLoad, since it's the load current. Now we need to run a series of simulations. I will vary the modulation index from 0.1 to 3.5, and we will see exactly up to what value of MA is the output voltage linear and from what point it starts to saturate. So for that, let's go back to the Simulink or the MATLAB script that we started writing. So let me modify. So this is simulation setup. Let's name the model to be 8 cell X. This we will need later. I mean, we don't need it anymore. And let's call it directory. So all the output variables that I want to save for output voltage, let's call it all Vout, and then it should be, let's initialize, we have to one number of runs. Of course, I forgot to calculate beforehand what that number of runs is. So as I mentioned, I will vary the modulation index from a minimum value, which would be 0.1, or I will specify it later, but let's run it up to 3.5. I would like to take a step as well. That means I will vary MA every 0.1. Yep. And the number of runs that we can easily calculate as also specified here. It is just a, but this is not how I am going to initialize. I will go for number of runs. So I have the maximum of 3.5, step is there. Of course, values, we also need to take how many, as I'm in the range, I need to specify, which is then, let's call it MA values, and should run from 0.1 to, let's take it from 0. I will change it to other values if we have problems at 0 modulation index. And then it's going to, with each step, yeah, and the maximum value. And now the number of runs, that means how many times we're going to run the simulation, is calculated according to the length of MA values. Yep. Now we can say for this number of runs, we can set the output voltage window. We just initialize it to this. So we pre-allocate the space for this variable, so to speak. Now we can write a loop, a for loop, which runs from 1 to, it's already suggesting me to do that. And MA should be each value from MA vals that I defined. That's right. Run the sim. This is very clever actually. It suggests me what I'm going to do actually. It's really interesting. So MA is first run the simulation for current modulation index. Yeah. Let's just forget this. So MA, we just read it from our vector above, and what I am going to assign to the simulation workspace. So that means let's take assign. What is it? Assign in base. What are we going to assign? The variable MA. The MA. That means we are sending the variable to Simulink NK workspace. And then we need to simulate our file. So simulate, let's say, model name. Since we have already defined, so simulate model, for example. Now, after each simulation, the results of the output voltage is going to be sent to the workspace, and we need to read the value from the workspace. To do that, let's call it the data first, and we have to read the value. So first one was Vout. This is how we named our variable. Ans is going to be also read from, it's a way to read the data that's simulated and sent back to the Simulink or MATLAB workspace. So with ans and Vout, what we need is a semicolon, of course, and data. The first data was for voltage, and let's call it I for current. It's .I load. I load. Now we're going to store the data. And what is this next suggestion? I think Copilot is quite genius. So this should be all out. all out I is equal to data. Yes, store the output voltage for each modulation index. Exactly, that's what I want. What I also want is all, I didn't define that variable yet, but not k, it's I, is equal to data, and I'm going to read it from I. Yes, let's define that variable as well. All I, number of runs, save it. I have read the data. And we're going to plot the waveform right away, just to see that here for each simulation run. And for that we need to plot data dot time, since we have saved, there's a time series, and then data dot data. It should be enough. No, it's, so let's display the name, and that should be, what is the syntax, as printf and underscore a is equal to 0.2 f, and we want to show, of course, the modulation index. So what's going on now? We need to save the output variables. Since it's going to be messy for a lot of simulations, I should have defined a folder to save the variables. And let's do it here to save. So I'll call it save the output result in a folder. Yeah. I'll call it output directory, full file, present working directory, and I would like to save under a folder called results. Yep. So if, for example, the folder doesn't exist, that this output directory doesn't exist, let's create one, make directory, output directory, and close the if condition. Save the run, for example, save each run full file, output directory, printf vout. Let's take the format so that we have vout underscore 1 is the first run simulation, and then it continues increasingly. So vout, to show the number, it's a percentage %d for integer, and let's save them in format of .mat. It's better actually to save from 0, so we can read them. So to show that in terms of 0, it says comma I minus 1. So we're going out, then we have to save it as data. And we have to do it for the current as well. I'll just call it iLoad. And of course, we have to read from data underscore I. So this is for all output voltages, and the second one for all load currents. Now we can close our for loop. So did I forget anything? Let's check. We have the initialization. Now, since we're running a batch simulation, this MA, the initial value, is going to be overwritten what we have defined here. So I'm running from 0 to maximum, which is 3.5 of MA. Number of runs is the maximum of the values. Yeah, that's correct. Your model name is this. I have pre-allocated the variables so that we can save them here. So data is for output voltage, and we're assigning to the workspace using this command and saving all of them there. Okay. If we run them, is there an issue? This one? Is it an extra subplot is here? Usage might be invalid syntax. Where? I don't see any okay, this might be for that extra comma. Yeah, it's now gone. So you see in under this we don't have result folder yet. If we click on run, let's see. So the results folder is then created and simulation seems to be running. Is it complete? This is for the last one. It's a 0. Okay. Let's go through it again. So as print is the first error, there is no variable. I forgot the F. So is it for individual curve? Or it's even better to look into here. So that means for all of the cases that we defined, a simulation is being run. You see the sinusoidal curve is getting higher in terms of amplitude than the triangular wave. This is because with each simulation the modulation index is being increased. So red is the triangular wave. You see it's remaining smaller and smaller with the forwarding simulations, and MA is now around 2.1. now it's 2.2, 2.3. It should continue until 3.5. Let's just wait a little more. Good, it's now complete. So the last simulation is that for 3.5. I see the sine wave is done for 3.5. Now what we need to do is post-process the data. Let's check if they are there. So previously these output results were not there. So we have the load current running from 0 to 35 and output voltage 0 to 35. So there are in total 36 simulations. Let me check. Num runs, so 36, as we expected. Now is the point to post-process. That means we have the variables here, and we have to plot MA along the x-axis and V output along the y-axis. But since that is still a long video, I would like to stop here and continue with part 3. So in part 3 we will see how to write a code to analyze this MA versus fundamental component of the output voltages and currents. That means we'll have to run a calculation for the output voltage, to how to calculate the harmonic components as well. So we'll write a function for that and calculate and plot them there. So see you on the part 3. Thank you.